earlier we have shown that given a symmetric form on a real vector space or a Hermitian form on a complex vector space, we can always find an orthogonal basis. Okay. And then we stated that the Gram matrix of this orthogonal basis would be of this form: I P minus I M and I Z, or not I Z, excuse me, 0 Z, yeah, 0 Z. Okay. And then we are proving that these numbers, well, of course, where this is P plus M plus Z cross P plus M plus Z, that is, okay. This is an n cross n matrix, a Gram matrix, where n is equal to P plus M plus Z. Okay. And then we are trying to show that this P, M, Z are uniquely defined given the Hermitian or the symmetric form. Okay. And we have shown only that this part is uniquely defined because Z is the, well, Z is the dimension of this. Okay. And this definition only dependent on, so V perp was uniquely defined given the form from V cross V to C or to R. Okay. I mean the Hermitian form or the symmetric form, whatever is given to you, whichever is given to you, this, I mean given the form we have a unique definition of V perp, and so this Z doesn't depend on the choice of the basis. Okay. You can choose any orthogonal basis, and not orthogonal, orthogonal basis, and then you have a part of it with made up with the vectors which are self orthogonal. Okay. Manish, is this fine? Okay. And then we are given this n because we know the dimension of the space, whatever is given to us, and then the form, so V perp. In particular, that means we are given n and we are given Z. So that means P plus M is given to you. Okay. Now we are trying to show that this P and this M are also well defined given the form. Okay. So claim P and M does not depend, do not depend on the choice of the orthogonal basis of V with respect to the form, the symmetric or Hermitian form from V cross V to R or V cross V to C, depending on whether V is a real or a complex vector space. Okay. So if it is a real vector space, we take it as a symmetric form. If it is a complex vector space, we will say that the form is Hermitian. Okay. For which we are going to prove this claim. Okay. All right. So suppose now we have an orthonormal basis with respect to which the Gram matrix is of this form. Okay. So this, let B and B dash. So this is the proof that we already started. Okay. let B and B dash be two bases actually, two orthogonal bases of V, and let the gram matrix of the form with respect to B be this one. Okay. And also let GB dash be equal to some I P dash I minus I M dash and 0 Z. At least we know that Z is fixed, okay, where Z is equal to the dimension of V perp. Okay. So we are trying to show, the claim is to show that P is equal to P dash and hence M is equal to M dash. Okay. Till now we know, we have shown, from the previous class, that P plus M is equal to P dash plus M dash. Okay. Of course, this is equal to N minus Z, that is dimension V minus dimension V perp. Okay. So it suffices to show that P is equal to P dash. Okay. It is just going to show that P is equal to P dash, and then that would imply that M is equal to M dash, right? So let B be equal to this one, V1 dot 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 VP VP plus 1 dot 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 VP plus M and the rest. Okay. VP plus M plus 1 dot dot Vp plus M plus Z. Okay. And let B dash be V1 dash dot 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 Vp dash or V dash P dash V dash P dash plus 1 dot 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 V dash P dash plus M dash and V dash P dash plus M dash plus 1 dot 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 V P dash plus M dash plus Z. Okay. So given these two things, all you know that this one P plus M and P dash plus M dash, these are the same. Okay. Now let's consider this set. Okay. Let's consider this set. Let's consider S, which is V1 dot 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 Vp and V dash P dash plus 1 dot 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 V dash P dash plus M dash. Sorry. This set of vectors. Okay. So it suffices to show that this set is linearly independent. Okay. That would in particular imply that this set of vectors and, well, what it will do. I mean, why it suffices? Tell me. Here p plus in this p plus m dash vectors. Yes. No. Yeah, we know that it is. We have till now p plus m is equal to p dash plus m dash, right? Yes. So here is p plus m dash elements, right? So the total number p plus m dash, right? If it is linearly independent, well, all you can say is that the cardinality of this is less than p plus m. So you get that p plus m dash is less than p plus m, right? And that in particular would mean what? So p plus m dash is less than equal to p plus m because it is in the space which is spanned by this one, or I mean which is, well, wait a minute. Yeah. So take the space which is spanned by this and this or this, because we have here this is I mean no. Wait a minute. We are, well, till now we are trying to we have shown that this is dimension v minus dimension v parp, but we have not shown that they are spanning the same set, right? Okay. So, well, let's write this as, all right. So now till now we have shown that p plus m is equal to p dash plus m dash, and call this some r. Okay. This is the, I mean, this is the number of vectors which are in the basis which are not in v parp. Okay. And then the cardinality of this set is, well, this is just r minus p, right? So m is then r minus p, m dash, and r minus p dash, and so the cardinality of this set is, so that implies the cardinality of S is equal to, we are denoting cardinality by this or like mod, just this. Okay. So the I mean that implies the cardinality of S is equal to p plus r minus p dash, right? Okay. And then note that this set of vectors is, I mean, this set is not in v parp, right? So the claim is that then this is less than equal to r. Is that true? Why? If we assume that p is not equal to p dash, right? Yes. Yeah, actually this will show that p dash is greater than equal to p. Okay, you want to start with the assumption that p dash is greater than. Okay, yes. Yes. P minus, okay, all right. Let's write it down somewhere. So if P is not equal to P dash, that is we are trying to prove that P is equal to P dash, right? So let's start from the assumption that they are not equal. Okay. Without loss of generality, we may assume that P dash is greater than P, right? P minus, yes, all right. P minus P dash is, right. R plus P minus P dash is less than R, of course, yes. Then that would mean that P plus R minus P dash is less than R. So that would mean that these are spanning, this thing is spanning a set whose dimension is less than R. But how does that lead to a contradiction? Yes? S is greater than? Yeah, I mean, well, at first it doesn't, I mean, you have two bases. So you can call one base B, another one B dash. So that means if that is not true and if still some, I mean, if your P is larger than P dash, just name the bases in a different way. Okay. Yes, Kaushik. V minus V perpendicular, we have not defined that. V minus V perp. So what do you mean by V minus V perp? So V perp is a when? So then the question becomes, when can we write V is W direct sum W perp? What was the condition on W? Non-degenerate. So in particular, V perp is not such a space, right? So we cannot decompose it as V perp direct sum something else. Okay. So this requires I mean this requires and it suffices actually. So this is a sufficient condition that the form is non-degenerate on W. Okay. All right. So the question now becomes is that whether considering this set would suffice to show that, I mean, if we could show that this set is linearly independent, whether that would suffice to show, I mean, whatever the claim is, that is P is equal to P dash, that is whether we are getting a contradiction. So at first, well, let's leave it to you for thinking for a while, whereas let's try first to prove that this set is indeed linearly independent. Okay. So suppose it's not, okay, what happens? All right. So suppose S is linearly dependent. That implies there exists a linear combination. There exists A1 dot 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 AP and B1 dot 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 BM dash in in whichever field we are considering. So we are considering C, such that A1 V1 plus dot 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 plus AP VP is equal to B1 VP dash plus 1 dash plus dot dot plus BM dash V dash P dash plus M dash. Okay. And this is going to give us a contradiction. How? Such a linear relation, I mean such a relation between the elements in the first part of the basis B and the second part of the basis B dash would lead us to a contradiction. So what are the specialities of these basis elements? Well, they are orthogonal to each other, and what else? Vi is 1, right? And here minus 1. So if you name this as V and consider this, what happens? Look first at this expression. What do you get? Yes. So what is VV? You are just expressing it like this in terms of this orthogonal basis B. Sum of the mod of the coefficients, right? These are assumed to be complex numbers, and so your form is Hermitian, and therefore this one would just give you sum over AI squared, I running from 1 to P. And what do you get here? Exactly, right. So here we will get summation Bj squared j running from 1 to m dash. Okay. So this is something positive and this is something negative. Okay. So this is only possible that both are 0. Okay. Each of the coefficients is 0. Right. So that would imply that A1 equal to A2 equal to dot AP equal to B1 B2 dot 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 equal to Bm dash, that's equal to 0, right? Okay. All right. So now what to wipe? The left part, can we wipe this out? Thank you. So that would mean if you call the span of this, given P, if you call say W1 the span of the first part V1 dot 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 Vp and W2 as the span of Vp plus 1 dot 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 Vp plus m, and similarly if you consider W1 dash as the span of V1 dash dot 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 V dash P dash, and W2 dash is equal to span of V P dash plus 1, sorry, V dash P dash plus 1 dot 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 V dash P dash plus M dash. What did we just show that there? That this one and this one are linearly independent, right? So you can fuse their bases together and you will get then a basis of what? So if, I mean, this one that you are considering, instead of this set, if you take an ordered set, then that would give a basis of which space? No, in terms of W1, W2, I mean this new spaces that we defined. Right, the direct sum of W1 and W2 dash, because only for direct sums we have seen that you can augment the basis and you get the basis of the direct sum. And this was an if and only if condition on direct sum, right? So then the set that we have defined there, so dimension of W1 direct sum W2 dash, this set is becoming a basis of this, the ordered set instead of S, of course. Therefore, the dimension of this is equal to what? P plus M dash. Okay. And what is the dimension of similarly W1 dash plus W2? It is P dash plus M, right? So now the first part of this basis and the second part of this basis, the same, right? You can apply the same logic and you get here P dash plus M, right? Now note that if this set, well, at first, does this set have any intersection with V perp? It cannot have an intersection with V perp, right? And if it cannot have an intersection with V perp, we'll be done. So can you complete the proof after, I mean, from this onwards? If not, then let's talk about this again. But try to complete the proof from here. Okay. So check that these things I check whether W1 direct sum W2 perp or W1 dash direct sum W2, whether these are independent of this. Okay. And once you could check this, that would complete the proof. So this was an exercise in Artin, right? Yeah. Yes.
I claim that if I plug, say I consider the space W1 direct sum W2 direct sum V1.
Okay.
Right. So I know that
W1 direct sum.
W2 direct
Okay.
sum V1.
Yes.
I know that they are related.
Okay, just a minute. I will write it down what you are saying, but where? Yeah. Okay. So you are considering W1 direct sum W2 perp or W2 dash? Dash. Okay. Direct sum V perp. Okay. I mean, if they are independent, you can consider this. Yes. Right.
Can show that they are independent.
Yes.
And we assume that M is greater than equal to M dash.
Yes. So this should exceed n.
Yeah. This will
That's not possible, right? So basically, you are
greater than equal to M.
exactly.
Then that is like P plus M dash plus Z.
So dimension of this would be equal to P plus M dash plus Z, and that is equal to P plus M plus Z. So you will have M and M dash equal. Okay. The same for the other one as well. Okay. Yeah.
We could also take S and append the elements P dash by N dash is 1 and the
Yeah.
basis of V1 from
So
the.
you take S and yeah. Again, tell me.
So we take S.
Yes.
We append the elements of P dash by N dash plus 1 and so on.
People. Okay. Yeah. Right. Yes. Yes.
So we can again show that that set will also
Yes, how?
Like the same method.
Okay, so that means you are separating this on two sides of the equation, and then
We know for those elements v dot v is 0,
yes.
and here it is non-zero, so
No, but it is positive and this is negative. So there may be cancellations.
if we fix them to be 0 first,
I mean, this one is definitely giving you 0, right? But if you express it in terms of these ones, then it's not clear whether that would give you 0 or not. I mean, if they're of all of the same sign, then you can say they are positive or they're negative. But if it's a combination of both signs,
we fix the coefficient of some of the terms that v dot v where if fix
yeah,
them to be 0, is that like
which, no, no, it's, I mean, that you are not given that liberty of fixing the coefficients of this to something. All you know that they're, I mean, if you take the product of themselves with, I mean, v1, v1, v1 dash, v1 dash, for example, that will give you 1. And instead, if you take a vector from here, the inner product of that with itself would give you -1. That's given to you. No other control over the coefficients. All right. So let's, okay. I think we can wipe this out, right? Okay. All right. Now, another exercise. So from this exercise, we are left with this part. Okay. And now there was another exercise, that is exercise 2, say, let A n cross n be a complex matrix, a Hermitian matrix, sorry. That is, A is equal to A star. Okay. Show that. Okay, before even we write show that, we have to define some more things. So some submatrices of A. So let A1 be defined as just this entry A11. Okay. A2 be defined as A11, A12, A21, A22. Okay. And similarly, AK is this matrix Aij. Okay, just to keep that notation similar, square round brackets here. So Aij, I less than equal to K, J less than equal to K. That submatrix. Okay. So which submatrices we are considering? This is just A1. Now this one, this entire thing is A2 dot dot dot. This, I mean, the K cross K1 is a K. So this was 1 cross 1, this is 2 cross 2, and this is K cross K. Okay. And the entire thing is then n cross n. Okay. That is, so in particular, an is equal to A. Okay. So we define this, and then the claim is that this matrix A, the given one, is positive definite if and only if the determinants of all of this from A1 to AK are positive. Okay. Show that A is positive definite if determinant, if and only if determinant AK is greater than 1, so not greater than 1, greater than 0 for all K. Okay. All right. So one way the claim is trivial. Which way? figured that out by the time we clear the board? Yes, how? Right. Why it is trivial? It could
Consider the subspace corresponding to
it could also be negative, not only 0. I mean, so you have to remove both the cases. So we are not even given that these are greater than or equal to 0. You have to show that these are all positive. Okay. So you have to, you have to take the entire other case, that is, it is less than or equal to 0, and show that that is not possible. Or you can prove it directly from the definition of positive definite. What? If A is 0, the question is that whether A can be 0. If it is if it is a positive definite matrix, so what is the definition of positive definite matrix? That for any non-zero x, right? So let's start it from the x. Okay. So A is positive definite if and only if x star Ax is greater than 0 for all x not equal to 0. Okay. Right? Since it's a Hermitian matrix, we know that x star Ax is real for all x non-zero. Okay. And of course, for all for x equal to 0 as well, it's 0. Right? So now that's the definition we are starting with, and we would like to show that Snehmo's guess was correct, that if A is positive definite, that these matrices all have positive definite, positive determinant. That's rather simple to show. So the first one is this one. Okay. So now what does it mean exactly to say that a matrix is positive definite? What can you say about the inner product? All the diagonal elements. Is that will that suffice? So think in terms of orthogonal basis. What can you say? At first, what can you say about the form? It's a Hermitian matrix, so the form is Hermitian, that's given to you. And if it is moreover positive definite, then the form is it's an inner product. Okay, so you can define the length of any vector, and therefore you can apply one of the process that we have seen earlier, Gram-Schmidt process, which will give you an orthonormal basis. Okay, so if A is positive definite, the corresponding form has an orthonormal basis. What would be the Gram matrix with respect to that? Not only diagonal matrix, identity matrix, right? Okay. So if A is Hermitian, then yeah, sure. So we are just writing everything that we have just said. Okay. So if A is Hermitian, now choose any set of linearly independent vectors over the. Suppose V is of n dimension. An n dimensional space, and to choose a set of linearly independent vectors, and suppose A is the Gram matrix of the form with respect to that set of vectors. Then that gives you a positive definite Hermitian form over that vector space, right? So if A is Hermitian, then the form that it defines with respect to a basis. Now this could be any basis, okay? A basis of complex vector space V is Hermitian, right? Since it's a Hermitian matrix, the form should be Hermitian. Again, Monideep, what you are doing, you are choosing a complex vector space, you are choosing some basis of it. And you are defining A to be the Gram matrix of the form with respect to that basis. Okay? Since A is Hermitian, in particular, that means the Gram matrix is Hermitian, that would imply that the form, now if you have defined the Gram matrix, that defines a form, right? Because the coordinate vectors with respect to that basis, whatever you have chosen, would now just multiply around A in this form, this manner, and give you the output of the form with respect to, I mean, if you are having V and W, then this would just be X star AY, where V is equal to Bx and W is equal to By, right? So now if your matrix A is Hermitian, this form is going to be a Hermitian form. Okay? And moreover, it's given that your form is, your matrix is positive definite. So that would mean that this is not only a Hermitian form, it's a positive definite Hermitian form. Okay? Moreover, since A is positive definite, the form is also positive definite. It simply means that if you put the same vector here, that is, if you are getting X star AX, that is positive. That's the definition of a positive matrix. Okay. The form is also positive definite. Okay. And that would mean that phi Gram-Schmidt an orthonormal basis. Phi has an orthonormal basis, okay, because it is a positive definite Hermitian form. In other words, an inner product. Okay. So, determinant of exactly, yeah. So therefore, the Gram matrix with respect to the, yeah, just 1 minute. The Gram matrix with respect to the orthonormal, the Gram matrix of the form, of course, of the form which was defined by A, okay, with respect to the orthonormal basis is identity. Okay. Is identity. All right. So, yes.
And if we take A1 and A2 as that, then it also gives us the subspace upon which the form is defined.
Right.
Now we know that that subspace is also positive definite
Perfect.
according to that form.
Indeed.
So P star AP is
Yes.
equal to identity.
Right.
for some cases.
Sure.
Take determinant of both sides.
Wonderful. That's the logic. Okay.
So
Okay.
that would imply that determinant of AK is greater than 0 because
Right.
determinant of P star and determinant of P are conjugate of P star.
Exactly. Yeah. So for each space, then you are getting that this is greater than 0. So let's again write it down what you just said. So this is identity. That means if you are going, so at first you have chosen a vector space and a basis of it, right? And then over that A defines an inner product. Okay. Now you know that there exists some other basis with respect to which another basis which is orthonormal. So with respect to that basis, the Gram matrix is identity. Now, how do you change the Gram matrix from one basis that you have chosen earlier to this orthonormal basis? P star AP, right? So that would just mean that P star AP is identity for some P in GL and C. Is this point clear to all of you? If not, please, Tushant, please let me know that whether till this you are with me, or if you have, at some point you left off. So we were having orthonormal basis of V, and the form was defined by this matrix on that vector space V with respect to some basis. This is the Gram matrix of the form with respect to some basis B. Now we are making a change of basis. Okay, making the change of basis by this P, which is the change of basis matrix. P is the change of basis matrix. Okay. And then this, the matrix of the form changes by P star AP that you have shown earlier, right? Now we know that the new basis is orthonormal. So the Gram matrix with respect to the new basis would be identity. Okay. So that's how we are just getting P star AP is identity. Okay. And now what we are going to do, take determinant on both sides. Okay. That would give you here. So what is determinant of P star times determinant of P? Determinant of P star times determinant of P. This we are having on the left, well, of course, multiplied with determinant of A. And on the right hand side, you are just getting 1, right? So now, please tell me what is this determinant of P star time? Right, because this star is bar transpose, right? So determinant of P transpose is equal to determinant of P, right? And this, now you are taking the bar of it, so it is the conjugate of that. Okay? And therefore, this is just determinant of the conjugate of determinant of P, okay? Which will be determinant of P, determinant of P squared, this one, okay, times determinant of A, that would give you 1. Okay. That is giving you 1. In particular, that would mean that determinant of A is positive, right? Because this is positive, this cannot be negative. Right? Okay. So that implies determinant of A is positive. Okay. Now note that if instead of considering the entire basis of V1, V2 to Vn, the initial choice of basis, say, if you restrict the basis to just to the first vector, say V1. Okay. So with respect to V1, what is the what would be the Gram matrix? A11, the first entry only. Okay. This one. This is the Gram matrix. If you just consider the operator defined by A, not the operator, the form defined by A on the span on the space defined by the span of the first basis vector. Okay. So what we are saying here is that with respect to a basis, say this is B and this is V1 dot Vn. Suppose your initial basis was this, okay, and now consider the form, the restriction of the form on span of V1. and let V1 be the, consider the basis, and well, span of V1, then the gram matrix of the form with respect to the basis V1 is just A1, where A1 was defined here. It's just A11. Okay, that's the gram matrix. This is V1, comma V1, right? That the inner product. Okay, and the same argument runs, right? Because A1 defines, this we restrict the form to a subspace, and the form is given to be a positive definite Hermitian form. It is so also on a subspace, right? And therefore, the same argument gives you that determinant of A1 is positive. And not only that, if we restrict the form to some set, subset of these vectors, so V1, V2 to V, some VR, say, you will get, so consider the restriction of the form to the span of V1, V2, dot, 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 Vn, or not Vn, some Vi, okay, some I for some I less than equal to n, okay. Okay, then the gram matrix with respect to the basis, gram matrix of the form with respect to the basis V1 dot 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 Vi is just AI. Okay. Just the first part of this. Okay, you are considering only this part, and what are those ones? These are just Vi, Vj, where I and j both are less than equal to k. Exactly this one. Okay, and you know that the form is symmetric, positive, sorry, Hermitian, and its positive definite form on this span as well. Yes, Manideep.
So like I had an idea. If I was thinking like if A equals to A dagger,
Yes.
Hermitian form, we have proved that all of its eigenvalues will be positive. We can
Have you proved that already?
I mean sir, A star A.
Or where did you prove this?
I said A star AX. If AX
But you said that you have proved this. So did you prove it in the class or in the tutorial?
maybe the tutorial.
You have already proved this? Great.
I not like somehow maybe if not I'm sorry. Like
Okay.
if Ax equals to lambda.
So if you have proved this, you know how to prove this, right?
Yes, sir, Ax equals to lambda is
Yes.
taking lambda.
Yes.
So lambda is greater than 0. Maybe like
Okay.
rudimentary.
Yes.
All of its eigenvalues are positive.
Yes.
Determinant of any matrix is a product of all the eigenvalues.
Right.
So if all the eigenvalues are positive, then determinant is positive.
All right.
One side is like the other side I don't know.
Yeah, because the thing is that if you restrict this to the first case, it's not necessarily the eigenvalues. These are not the first k eigenvalues. So the other way you cannot go in this manner. Okay. Yeah. But nevertheless, if you restrict the gram matrix to the first few, not matrix, the form to the span of only the first few vectors, then you are getting this submatrix, right? The submatrix AK. The proof is then exactly the same, because then some pk star AK pk would be ik. Okay. It will have an orthonormal basis, right? Because the restriction would also define an inner product on the span. Okay. The span is also a vector space on which you are getting a positive definite Hermitian form. Okay. Okay. Is AI. Okay. So that would give, as before, that determinant of AI is greater than 0. Okay. For all I less than equal to n. Okay. Now the other way. Okay. The other way means that suppose we have this this assumption that the determinant of AK is greater than 0 for all k. We will now go back, okay, to show that this is positive definite. This matrix A is positive definite. Can I wipe this board out? Are people still writing? Okay. So this was the easier direction. Okay. Now the non-trivial direction, that is, let determinant of a k be greater than 0 for all k less than equal to n. We must show that, okay, to show a is positive definite. Okay. All right. We'll prove by induction. Okay. For the first one, it's simple, right? If it is 1 cross 1, there is nothing to show. I mean, it just means that a1 times the square of anything is positive. So, or the absolute value of anything squared is positive, and that means that a11 is, well, no, the other way. So, if we do not proceed by induction, then what is the way? Yes. Yeah, okay. So you are given, it's a Hermitian form, right? So you have P star AP, AP is some diagonal matrix T, right? Okay.
Now the diagonal we know that we can reduce it to 1z minus 2z in the diagonal.
Sure.
So we
Yes.
take determinant both sides.
Yes.
We know that determinant of A is greater than 0.
Yes.
So the determinant of B should also be greater than 0.
Right.
So it should only have ones in the diagonal.
It will only have ones on the diagonal. Sure.
The
Yes.
form is positive determinant.
The form is
Positive determinant.
okay, but then you are saying that only the determinant of A is positive greater than 0. That suffices. Does it?
I don't know, but I mean it works, right?
Okay. Let's see. So let V V1 to Vn be an orthogonal basis because it's a Hermitian form. Okay. Okay. Wait a minute. I write this out because we have written the conclusion of this at the beginning. So let's wipe this out and write it clearly. So this could be our first attempt. Okay. So let V be V1 to Vn we have started with this basis already earlier, so maybe we take some other basis, okay? Because we defined the form of A, but that was the other part. Okay? So we can actually start with this, and then we can assume that this is an orthogonal basis. But when we are taking an orthogonal basis, we are talking about a vector space already, and well, I mean A defined a Hermitian form with respect to some basis on that, right? And we assumed that this was the first choice of basis of V. So this be a basis of V with respect to which A defines a Hermitian form. Okay. And now what we are saying that let B dash, which is defined as V1 dash dot 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 Vn dash, be an orthogonal basis of B of V such that the Gram matrix, okay, we write there on the left side. Okay. such that the Gram matrix is of the form IP minus IM 0Z.
That would come into use. Determinant of AK is greater than 0 because we don't know whether n is even or odd.
Yes,
So it would come into use.
right. Yeah.
So
Okay.
then we know that we can reduce it to that form.
Yes.
So P star AP is determinant of
Right. So P star AP. So if a P in GLN C is such that B dash is equal to PP, then P star AP is equal to this one, okay, IP minus IM and 0 Z. Okay.
we at least know that OZ, I mean that part would vanish, but Z should not be there.
Yes.
So it would only have 1Z minus 1Z.
It would be IP and IM.
Now
IP and minus IM, right.
we get the determinant of A is greater than 0. That first mean that
That this
M is even.
M is even, right.
That,
Yeah.
that's it. But now we also know that determinant of AK is greater than 0.
Yes.
We can apply the same logic to some subspace,
Yes.
right?
Right.
I mean, if we know that Gram matrix, say A is not B1,
Right.
we know the columns.
Yes. The thing is that whether you will have the, I mean, P and the Gram matrix of the, well, whether only the first part of each of the matrix will work out, that's the question then. So what I want to say is that now you want to conclude something about, so at first we are having that M is positive, right? Let's write it down, everything, because I think if we are just conversing, maybe many of the classes, many persons in the classes. Exactly, yeah. So let's write down all the logic and then, so this is our first attempt, okay? And it was a very nice attempt because we just saw the previous result, okay? So indeed, it's quite nice that you are already trying to apply this. Where should I? By the way, I must tell you, I mean, before we go into seeing more of this proof, just two small definitions which I forgot to give you earlier. One is signature of a form. Okay. So if you are given a signature of a Hermitian form, Hermitian or symmetric form, it's related with this. Okay. So I mean, it could be that you are given just a form and you were asked to find the signature of the form. What is that? It is just P comma M in this case, okay? Because given a Hermitian form, you can get an orthogonal basis of that, right? And we have shown that for some basis you will have such a thing where this P, M, and Z are well defined. I mean, it doesn't depend on the choice of the basis. Well, you have still some part of the proof left for you as an exercise, but that's doable. Okay. So this one is called the signature of the form because Z is uniquely defined, right? Z is a dimension of V part. Okay. And what else? Now, just a, short detour. So given a form, how do you get its signature? Given a form, given such a form, also another notation I must give you, a notation. I p comma m, this would be defined, I mean this will, by this will mean the first part. So I p m would be just I p and minus I m. Okay. So this is a notation, but nevertheless, now let's think about this. That is, given a form, a Hermitian form, how do you get its signature? How do you find out its signature? Consider the which basis? You need an orthogonal basis, right? Because you need the, so not only an orthogonal basis will get this diagonal. Okay. Still, you have to check that whether, I mean, what are the diagonal entries? So whether they're positive, whether they're negative, whether they're 0. Okay. So, and according to that, you could do, I mean, so you can scale each of them. For 0, you don't have to do anything. For the rest ones, I mean, for this one, you can just divide by their root of their norm, right? What will you do here for the negative ones? So if VV is negative, what should you do? So we are just trying to get a basis. You need not actually. You can just take an orthogonal basis and check the signs. Okay.
Divide by square root of minus
Square root of the norm or absolute value, because you know that is a Hermitian form. VV is real. Okay. So replace V with V divided by square root of the absolute value of this V comma V, square root of that. Okay. And this will give you some vector such that the product of this with itself is minus 1. Okay. So if you have an orthogonal basis, you can of course do this. And how to find an orthogonal basis when given a basis? Gram-Schmidt, yeah. That's, yes. Exactly. Yeah. So yeah, that was for the inner product basis. But you have seen that if you are given an orthogonal basis, you can define a projection on that. Okay. So at first you have to check whether you are getting a vector at all whose product with itself is not equal to 0. Okay. If all are 0, I mean all the vectors whose product with itself is 0, you can neglect that and you can start. I mean the first thing that you for which you get some vi is not equal to 0. Where should I write it? There maybe. So the first vector for which you are getting vi not equal to 0, take that to be the first element of your basis. Okay. And well, not equal to 0. Okay. Even if VIV is not equal to 0, you could still do something like this. You can still get the that V comma V equal to plus or minus 1. Okay. And do the orthogonal projection. Proceed. Okay. Proceed till when? Till the time when the remaining ones you're projecting. So at each stage, what we are doing, we are already having some space, some Wi, which is the span of the orthogonal basis that you have gotten so far, and whose products with itself are nice. I mean, nice means that is either 1 or minus 1. Okay. And then you are taking the next vector from your basis and projecting it over, say, Vk, projecting, or if this is Vi, then this should be Vi plus 1, and normalizing this. Okay. Now note that this was allowed if your base, I mean, if your form is an inner product. Okay. Here you are just given some arbitrary form. Okay. So this, I mean, these ones, you sometimes you have to replace it with the you have to take the wait. You are taking the you're taking the projection on that, and then instead of taking the norm, sometimes you have to replace it with the square root of pi wi perp vi plus 1 pi wi perp vi plus 1 and again the absolute value of the output of the form. Okay, exactly what we were doing here. Okay. That would give you the plus or minus 1 things on the diagonal. But at some point you would exhaust all of this. Okay. And then if you project it, project anything else on this perpendicular, what would be the output? It would be 0. Okay. All right, and you cannot divide with these things. Okay. So you have to perform something like an orthogonal, something like a Gram-Schmidt process. Instead of normalizing each of the vectors with their norms, you have to do something like this at each step. But at the end, even as soon as you exhaust this p plus m things, you would get these projections are coming out to be 0. Okay. So then you don't have to do anything. You can just keep that part as it is. Okay. So that's how you will get a basis which is an orthogonal basis with respect to which the matrix is of this form. Okay. And if you are already supplied an orthogonal basis, all you have to check is the signs of the diagonal entries. Okay. Then the positive ones are corresponding to P and the negative ones are corresponding to M. The 0 ones are corresponding to Z. Okay. Put P and M together in a bracket, that's the signature of the form. Okay. Many of you are looking a bit sleepy, and I guess some of you also had to miss the breakfast. It's still till 10, right? So please have your breakfast. And we start with this proof again after the tutorial. Maybe we'll have a 15 minutes break, and whoever wants to come can join to see the end of this exercise there. Okay. Yeah, actually this one is just giving you that the determinant of this is, okay, so let's write it down here as well. So from here, let's at least finish this part of the first attempt. So this will just give determinant of P squared times determinant of A is equal to that thing, right? Minus 1 whole power m times 0. Now since, okay, 0 won't be there, right? So it would just be minus 1 whole power m, right? Because that is corresponding to the 0 is coming from here. So if this part doesn't exist, then it is just minus 1 whole power m. Okay. So since determinant A is positive, that would imply that m is even. Okay. So that's already a nice thing. That is, so you have already done some exercise. That is, if you are given a Hermitian matrix such that the determinant of that is positive, you have already shown that its signature will have the second part even.